Hi, my name is Taylor Renzi, and today I'm going to be exploring physics and springboard diving. So, overall, I'm just going to be looking at the peak forms and what is required of the perfect dive and how the physics concepts we covered in class relate to this. And by mastering these, divers are allowed to maximize their performance and their scores. And overall, I'm going to be looking at it in terms of the takeoff in the air and the entry and how this relates to kinematics, Newton's laws of motion, momentum, and even fluid dynamics. So first off, we're going to look at an example of a perfect dive and what form is required of this. So as you can see in this dive, some important aspects that allowed this diver to achieve such great scores is that he had a high elevation on takeoff, kind of jumping more up than out, which allowed him to get more height and more time in the air, proper mechanical form, vertical entry, and minimal splash. And this is all criteria that comes directly from the Olympic website for diving judging. So, first, upon takeoff, Newton's third law of motion just explains how the diver gets propelled into the air. For every action in nature, there is an equal opposite reaction. So, whatever the diver exerts on the board, shown here, is exerted back from the board onto the diver as normal force, propelling them into the air. When the diver bends their knees, loading like a spring, and pushes, extending into board, work is done on the board, a force is exerted, and then the same force is back, which is mg, the weight of the diver, plus that force of them pushing into the board. And that delta F allows normal force to exceed the weight of the diver, thus propelling them off the board. And as shown by net force equals mass times acceleration, if the net force is upwards and out, the acceleration will be the same direction. And if you see Olympic divers, you'll often notice that they have very strong lower bodies. And this is important because if they can push more onto the board, there's a greater net force, and then the impulse is going to be greater. As you can see, the impulse, the change in momentum is equal to F net times the time. So greater F net, greater change in momentum, and a greater acceleration and change in velocity. So, a key component of the takeoff is that divers want to jump more upwards than outwards, but in terms of physics, I'm going to be explaining why this is so important in relation to kinematics. So, say we have this diver with an initial velocity of 6 meters per second, and the height of the board is 5 meters, and we have one diver that jumps off at 45 degrees. Based on this, we can calculate the vertical component and the horizontal component. The horizontal is going to be equal to initial velocity times cosine theta, and the vertical is initial velocity times sine theta. And it's important to find these two components of velocity because horizontal and vertical will be independent of each other. So the only thing that determines when the diver reaches the pool, a 0 meter height, is going to be that vertical component, which is impacted by the acceleration downwards due to gravity. The horizontal component does not get acted on by this, and it is, in regards, we're going to say it's constant. So here we can see that at a 45-degree angle, the horizontal velocity is 4.24 meters per second. And at this 75-degree angle, it is going to be 5.8 meters per second, which is much greater. And then if we calculate time in the air for the two divers, you'll see that diver 2, who jumped off at a more vertical trajectory, has a greater time in the air of 1.76 seconds compared to diver 1 with 1.53 seconds. Another important aspect once in the air is that divers want to maximize their rotational speed for a majority of dives. And this isn't just because it looks cool, but also because it increases their time in the air. And this is explained by rotational and translational kinetic energy. So kinetic energy total equals kinetic translational energy plus that rotational. The rotational is the flipping motion as shown here, and the translational is that kind of up and down velocity. So mechanical energy is conserved when there are no net forces acting on the diver. And at the takeoff and during entry, these non-conservable forces are definitely at work, but they're rather negligible in the air. So we're going to be saying for this case that mechanical energy is conserved. So the kinetic and potential energy initial is equal to the kinetic and potential energy final, When the diver starts on the board, they are at rest, so the kinetic energy is zero. Um, but at the final, when they enter the water, the height is now zero, so the potential energy is zero. So this means that mgh, the potential energy, is equal to kinetic energy final, which is made up of kinetic energy translational and kinetic energy rotational. So as shown by this, say the W of kinetic energy rotational, which is equal to rotational velocity, were to increase as the diver flips faster. Since this is constant, this means that this component of the half mv squared must decrease to keep it constant. Since mass is also constant, the velocity thus has to decrease translationally. So this basically just means that a increase in rotational velocity causes a decrease in translational velocity, which means a smaller final velocity upon entering the water and a greater time in the air. So once a diver's in the air, it's really important that the diver is tucked and squeezing when they're trying to rotate as fast as possible. But when the diver wants to go into the water and minimize splash, go in at a lower velocity, they want to have the straight, extended as much as possible body position. And this is due to moment of inertia, which is how difficult it is to change the rotational velocity of an object about a rotational axis, which is determined by the distribution of mass relative to that axis. So say we have this diver who is 60 kilograms. They have a length of 2 meters when extended, and when they're squeezing, they have a radius as a ball of 0.4 meters. We can calculate the moment of inertia of this straight diver by treating them as a rod and using the formula 1/12 mass times length squared, which is 20 kilograms times meter squared. So if the diver wanted to increase their moment of inertia more, they would just extend as much as possible and increase that length component. But when the diver is tucked and squeezing, we treat it as a sphere, and we can calculate the moment of inertia as 2/5 mass times r squared, which gives us 7.68 kilograms times meter squared, which just shows how much the diver is able to decrease their moment of inertia by just changing their body position. So since momentum is conserved in this system, and L is equal to moment of inertia times rotational velocity, that W, if the moment of inertia decreases, the rotational velocity increases. So this diver would be able to flip faster. But if the moment of inertia increased for this extending position, then the rotational velocity decreases, which allows the diver to control their body position more and enter the water straight and with a minimal splash. So, when a diver enters the water, one of the biggest goals is to minimize splash because when the judges watch the dive, that's kind of the big thing they take away at the end. It doesn't really matter what the diver did before it. If there's a big splash, that's what everyone sees. So, a big component of what causes that splash is the force of drag. Drag is a force exerted by a fluid stream, which in this case, the water, which is felt by the object, the person, moving through a fluid. So it's kind of how the water resists the entry of the person. So divers want to reduce their surface area by going in this streamlined, extended position, hands first, as small as possible, to create less force and less of a splash. And this is shown by the formula for the force of drag. So FD, the force of drag, is equal to CD, the drag coefficient, times the area times the density of the fluid times velocity squared over 2. So this position will impact a few components of the formula for drag. So first, the coefficient of drag is dependent on the nature of the object and its shape. So the person that's extended like this will have a smaller coefficient of drag than a person in belly flop position or a tuck sphere position, which will allow the force of drag to be smaller. Also, this relates to the area, the reference area, which is smaller when the hands are extended out, decreasing drag. And finally, the flow velocity relative to the object, which is why we talked about how with moment of inertia and rotational kinetic energy, divers want to reduce their speed as they enter the water. So, in conclusion, what I take away from this is that physics concepts are directly applicable to each stage of springboard diving, whether it's Newton's laws of motion during takeoff and kinematics, or drag and impulse when the diver enters the water. By understanding these concepts of physics, divers are able to maximize their form, performance, and scores. And this just relates to all sports that athletes are able to increase their efficiency by being intentional with how they perform and train and understanding the physics of motion, which impacts every sport played.